Hi everyone, this poster is about the experimental and computational investigation of layer-dependent thermoconductivities and interfacial semiconductors of 1 to 3 layer tungsten diselenide. We used optothermal Raman technique in experimental part to use Raman laser as both heat source and temperature probing tool to obtain the relation between power and temperature in the 2D materials and then obtain the thermal transport properties. We then used full atom non-equilibrium molecular dynamics simulations in computational part to reconfirm the layer-dependent trend of thermoconductivities. During the measurement process, we took both laser power-dependent and temperature-dependent Raman measurements of the target 2D material. In general, laser is focused on the center of the suspended flake area, and the heat is transmitted along the radial direction away from the center of the flake. And we are considering measured temperature, laser power, laser spot size, absorption coefficient of the sample. First, we measure the laser spot size by moving laser across a sharp edge and feed the Raman intensity curve by error function. Here we obtain the laser spot sizes of the laser coming out of the two objectives. Thickness of 2D materials can be determined by atomic force microscope and Raman spectroscopy. We took temperature-dependent Raman measurement on these samples and then monitored the Raman peak shift, and then took laser power-dependent Raman measurement on these samples and obtained a relation between power and temperature, which are the highlighted part in this slide. We built a Python program to solve these equations by inputting more detailed partial differential equation solution methods in the code. And we can see that this figure 5 denotes the final calculated results for thermoconductivity of in-plane direction and interfacial semiconductors between sample and substrate with layer dependence. The full atom non-equilibrium molecular dynamics simulations were implemented on the atomic model to confirm the experimental result. There is a decreasing trend of thermoconductivity with the increase in layer number. The recent advances of mechanical assembly enable researchers to build heterostructure with different types of 2D materials with ultra-clean limit. Then we use the same measurement technique, studying the temperature rise of boron nitride encapsulated 2D material electronic devices. It shows boron nitride encapsulated structure provides very excellent heat dissipation. Our study will benefit device modeling, thermal management, and other applications.